you know, changes that occur to things like freezing points, boiling points, and it's basically a result of, as I mentioned earlier, having particles that are dissolved in that solution. So the presence of those particles basically get in the way of sort of the natural process where the solvent, if it was by itself, would be able to say freeze, to boil, and so forth. Obviously, as well, we saw something about vapor pressure affecting the vapor pressure of a solution as well. And really, ultimately, the more particles you sort of have in there, the more things that get in the way, and obviously a greater effect it has on those things. So another sort of property of solutions is one that is basically referred to as osmotic pressure. And basically, osmotic pressure is when we have sort of a solution that's separated from its solvent by a membrane. It basically allows, it will stop that flow of solvent molecules from one side to the next. So if you have sort of a, like a tube here, and say on, you have a membrane sort of in the middle, and on one side you got, say, salt water, and on the other side you have just regular water. What's going to happen through sort of the natural process of what's known as osmosis is basically the solvent molecules will move from a lower concentration to a higher concentration. So in the case of salt water, obviously it has something like maybe sodium chloride dissolved in it. So what we're going to naturally have is that flow of water molecules, which is the solvent molecules, basically flowing across the membrane into the more concentrated side, and really an effort, if you want to think about it, to sort of dilute down the other side. And basically, what happens is at some point, those water molecules that are coming across the membrane will basically stop. And that's basically when it reaches osmotic pressure, because from the atmosphere is basically pressing down on it, right? Pressure from the atmosphere is going to stop that flow basically of water molecules going from one side to the next. And for example, reverse osmosis is the process where you apply a pressure greater than osmotic pressure. So basically, what you do is you send the pressure down coming this way, greater than osmotic pressure. And that's going to force all the water molecules and stuff kind of back the other way. And obviously, if you have a lot of filters, you can filter out a lot of stuff that would not be in there and kind of filter out your water. But the normal sort of flow of solvent molecules usually goes from a lower concentration to a higher concentration, again, in an effort to sort of dilute it. We could actually calculate the osmotic pressure by doing this. This little symbol here represents the osmotic pressure. And really, osmotic pressure equals nRT divided by V. And really, this is just a fancy way of writing PV equals nRT. That's basically the equation we're dealing with here. This is P is equal to nRT over V. So it's really the ideal gas law we're dealing with here. And that means that obviously, if we use this to calculate the osmotic pressure, we want to make sure that we're in the correct units like we know it should be. Obviously, N should be in moles. R is our gas constant that we've used before. T obviously should be in Kelvin, and V should be in liters here when we use it. Now, you also see that the osmotic pressure equals capital M RT. M is molarity, right, which is moles per liter. And we also saw this as being really the ideal gas law when we're talking about gases, because if we take N divided by V, it equals P over RT. And that is our moles per liter, if you remember here. So that's our moles per liter. And that is really this part of it here, right? So if you take the N over V, that is the molarity and how we get to that equation there. So N over V is basically moles over liters, which is how we reduce this down to molarity times RT. So to do these sort of osmotic pressure problems, they really are ideal gas problems, and you just sort of solve for your osmotic pressure. So let's take a look at one here and kind of see how it all kind of works. If we want to know what is the molar mass of a protein that is 5.87 milligrams per 10 milliliters. It gives an osmotic pressure of 2.45 torr at 25 degrees Celsius. So again, just think about it in terms of units. We're looking for grams per mole. And we actually do have sort of the grams part. And it's right here. It's 5.87 milligrams. So obviously we do need to convert that into grams. So one of the things we would want to do is take 5.87 milligrams. There's 1,000 milligrams in a gram. And that will get us 5.87 divided by 1,000. Going to get us 0.00587 grams. So that is actually the top part here of our molar mass. So let's see what else we have left in terms of numbers. We have 10 milliliters, which is a volume. We have 2.45 torr, which is a pressure. And we have 25 degrees Celsius, which is a temperature. So that's all sort of our ideal gas law information, our PV equals nRT. If we just kind of check off what we got, we have pressure, we have volume, we have temperature, we always have R, and the only thing we're missing is N, which is moles, which is good because that is what we need to figure out the molar mass. So we're going to really use our ideal gas law here and solve for N, which would be PV over RT. We do have to do some conversions here. Obviously, we need to convert our 2.45 torr into atmospheres. So 2.45 torr, that is 760 torr is an atmosphere. And if we do that, we will end up with, we'll call it 0.00322 atmospheres. We also need to convert our volume into liters. So 10 milliliters, right, divided by 1,000. 0.01 liters. And lastly, our temperature into Kelvin. So 273 plus 25, going to give us 298 Kelvin. We now have everybody in the proper units here, so we can solve for N. N would be our pressure of 0.00322, our volume 0.1 liters, divided by our constant, which is R, and our temperature, which is in Kelvin. Everything's going to cancel out except for moles, and it looks like we will end up with, I think I missed a O there, 0.01. So that times 0.01 divided by 0.08206 and divided by 298, going to get us, looks like moles of 1.32 times 10 to the minus 6 moles. And that again is the bottom part that we need to calculate the molar mass. So we now have the top part, which is grams. We use the basically ideal gas law information there to get to moles. So to calculate the molar mass, we're just going to simply divide those two numbers. So 0.00587 grams divided by our moles of 1.32 times 10 to the minus 6 moles. Again, nobody cancels out in terms of units here. And we end up with, it looks like 4.5 to the 3 grams per mole. Any questions on that? About 4,500 grams per mole. It's a protein, so it's probably pretty big. Any questions on any of those steps? So the nice thing, I guess, about osmotic pressure type problems is it's usually kind of like an ideal gas law. So that's, again, stuff that we've obviously have done before. Any questions on any of those steps? Okay, so why don't you try one here and see what you come up with. Let's see what we got here. All right, why don't you give this one a go? We're also looking for a molar mass here and see what you come up with. And just like the last one, we actually have it a little bit easier in this one. It's actually already in grams, so it's actually good to go for the top number. And again, if we kind of go through, we have a volume, a temperature, and a pressure, much like the last one. That's going to allow us to basically figure out the bottom part, which is the moles, using our PV equals nRT. Again, here we will solve for N, which is PV over RT. In this case, pressure is good to go. Temperature going to end up at 298 as well. Volume, we're going to divide by 1,000, which gets us to 0.1 liters. So now we got everybody pretty much in the right units. So our N would be our 1.32 times 10 to the minus 3 atmospheres times our volume divided by our R, 0.08206. And our temperature of 298 Kelvin. Again, everybody's going to cancel out here except for moles. And looks like we end up with we'll call it 5.4 times 10 to the minus 6 moles. And that would be the bottom part. So this one's good to go here. So we'll go molar mass. It's going to be our 0.075 grams divided by our moles. And we will end up with probably a big number as well. Yep, 1.39 times 10 to the 4. Again, units don't cancel here. Grams per mole. Any questions on sort of osmotic pressure? Obviously, the more particles you have, the greater osmotic pressure you're going to kind of exert. Water, just pure water by itself, has no osmotic pressure. Again, it has nothing dissolved in it, so it has no particles. So again, the more particles, probably the greater osmotic pressure that you have. Any questions on osmotic pressure? Fancy word for ideal gas law type problems. Yes. Okay, so the next thing we're going to talk about is, up to this point, as I sort of mentioned earlier, and it was sort of a question that was asked in lecture. When we look at all of our solutes in all these sort of examples that we've done before here, they're all basically non-ionic. So they're pretty much covalent. They're all nonmetals together, carbon, hydrogens, oxygens, all sharing electrons, not going to be forming any type of particles more than just one per as it goes in for a swim and sort of dissolves. And that's not always the case when we do dissolve ionic compounds. And when we dissolve ionic compounds, we do need to take into the account that we are creating more particles. And since colligative properties are really related to the number of particles that are present, we do have to adjust for that. So at this point, all the examples that we sort of seen and all the formulas that we've seen have really been for non-ionic or covalent solutes. And again, what that means, as I just mentioned, pretty much for one of those guys that you go to dissolve, you get one particle. Now, if we were to dissolve something that's ionic, say something like sodium chloride, for every one sodium chloride that we dump in there, we get a sodium ion and a chloride ion. We basically get two particles for every one that we put in there. If we took something like, say, calcium chloride and dissolved it, we would get a calcium ion and two chloride ions. We essentially get for every one of those three particles that basically occur as a result of that. And to correct for ionic compounds when we dissolve those, we have to take into account, again, the number of particles are there, because that's basically the whole idea of how things are affected. And that's what's known as the von Hoff factor here. The von Hoff factor is abbreviated with an I, and the I represents basically how many particles you get. So if you think about everything we did before, which basically you get one particle per, I in that case is basically one, which is why we don't typically include it in those calculations because it's basically just one. If we were doing something like sodium chloride, I would have a value of about 2 for 2 particles that are there. If we did something like calcium chloride, the I factor would be a factor of 3. So where do we sort of insert these factors? They're actually inserted pretty much into the same formulas that we saw before. So if we took something like our freezing point formula, our boiling point formula that we saw before, we typically want to insert I into there, especially if we're dealing with ionic sort of solutes. So again, if you're dissolving something like sodium chloride, you want to take into account I. If you're dissolving something like glucose, which is carbons, hydrogens, and oxygens and covalently bonded, you don't have to worry about I because I is essentially 1. Any questions on that? So let me just kind of write where we insert those in. So our formula, say for our freezing point, was the Kf times M, and our formula for our boiling point was essentially Kb times M. Where you insert it is like right there. You just put an I and stuff. So I would be inserted in there, and we would use this for ionic solutes. Again, for sort of non-ionic or non-electrolytes, sometimes called non-ionic, non-electrolytes, I is basically equal to 1. And again, that's why we don't necessarily include it. Now, we can roughly, in most calculations, just go by the ionic formula and figure out how many ions you get and figure out the expected value for I, which is what this table sort of shows you. Again, sodium chloride breaks apart into 2 ions, and I would be 2. Magnesium sulfate also breaks apart into 2 ions, so I would be 2. Magnesium chloride, you get 3 ions. You get 3. You got iron 3 chloride, you get 4 ions. I would be 4. In reality, if you actually sort of did experimentally found, they are slightly off of those numbers, as you can see here in this column. So we don't really worry too much about sort of the experimentally one. You should know, I guess, that, technically speaking, they're not always exactly this number. But for any type of textbook calculation or calculation in this class or most classes, you pretty much could go by sort of the expected value for I when you do that. By the way, you could also insert I into those other equations that we saw for vapor pressure lowering. It just goes in front of the mole fraction and so forth. So you can use it in some of those other ones that we saw, especially the vapor pressure one as well. But these are probably the 2 most common probably ways that you'll see it. So everything works exactly the same way. The only additional thing is if it's an ionic guy that you're dissolving in that solution, you need to include I. Otherwise, you will be off in terms of your calculations and stuff like that. And again, we'll just go with what we expect I to be here. Any questions on that? And again, obviously, everything else in that equation is exactly the same as we've been talking about. Delta TF, change in freezing point temperature. KF is still your constant for your solvent, and M is still your molality. So if we look at sort of a problem here, the measured von Hoff factor, what is the measured von Hoff factor if 0.05 molality calcium chloride has a freezing point of minus 0.27? So why don't you take a second and try to calculate what I would be in this case and see what you come up with. Again, freezing point, just like we saw earlier, KF 1.86 degrees per molality. So take a second, see what you come up with. So we do need to take the I into account since that's actually what we're trying to find, just in case. But that, again, is a key for other problems. If you see something like that it's ionic, you got to take that I into account. Again, if you see something like we saw previously where it's just like carbons, hydrogens, oxygens, that's going to be non-ionic. You don't have to worry about it. So our sort of freezing point formula basically just changes by inserting that I in there, which in this particular case is actually what we're going to be solving for using the experimental information. They actually gave us the molality. Kf is actually, we could find in the table for water. We do need to find the change in freezing point temperature. Again, a reminder that this is not the change in freezing point temperature, but that is actually the temperature of where the solution freezes in this case. So as we did before, our freezing point temperature is going to be the temperature of the solvent minus the temperature of the solution. Again, water being our solvent here normally freezes at 0 degrees Celsius. In this particular case, it freezes at minus 0.27 degrees Celsius. That minus and minus is going to give us a positive 0.27 degrees Celsius, which is what we need here for our formula. We now have our change in freezing point temperature. So to solve for I, we're going to divide everything to the other side. So that's going to be the freezing point temperature change divided by Kf and M. That's going to give us 0.27 degrees Celsius. We're going to use our freezing point for water and our molality, which was given to us here. And what we see is Celsius cancels, molality cancels. It's just a number, which is good because that's what we're looking for in terms of I. And looks like we end up with 2.9 as sort of the experimental value for I for calcium chloride, which is pretty close to what we would expect it to be if we just look at our formula as we saw earlier. Again, going to break into a calcium and 2 chloride ions for a grand total of what we would expect it to be 3, which is pretty close in this case. Any question on sort of the von Hoff factor? Again, it's basically inserted into all of our sort of colligative property sort of formulas. Vapor pressure lowering, again, you just insert it in front of the mole fraction. Freezing point, boiling point, insert it in front of the freezing point constant or boiling point constant. And for calculations, you could just do it by the ionic formula. However many ions it breaks into total will be your I value. Any questions on that guy there? Question on freezing point, boiling point, any of those sort of colligative type properties? Okay, so to kind of finish up the rest of this chapter here, we're just going to talk about some other sort of properties of solutions, some of which we kind of touched upon here a second ago. They agree with me, so that's good. So first off, some of the things here, as we saw a little bit earlier, are talked about. Sometimes we do have a semi-permeable membrane, kind of like in cells and stuff. And basically, for a lack of a better description, it's sort of things that have really holes in it, and these holes basically allow sort of certain size molecules to pass. Things that are kind of too big aren't going to be able to obviously pass through to the other side. And there are certain things that are really large sort of solute particles, and those things are considered what are referred to as colloids. And those are usually large molecules like proteins or groups of molecules or ions that are together. Colloids are typically homogeneous, which means they look the same throughout. They don't separate or settle out because of that, right? It's like a homogeneous solution. If you poured it through like a filter paper, salt water would go through the filter paper. They're small enough to pass through filters, but they are too large to pass through membranes. We also have suspensions, which are heterogeneous type of substances. Heterogeneous, just like heterogeneous mixtures, means you see different sort of phases or layers. This is what this is as well, sort of non-uniform mixtures. They're often large enough you can kind of see it with your naked eye. They're trapped by filters and like membranes as well. So, if you took something like, say, sand and water, for example, if you try to pour the sand through a filter paper, it's not going to go through. It'd sort of be your suspension in that particular case. Sort of a super zoom version here of a membrane, as you can see again, sort of has channels, if you will, that's going to allow certain size molecules, say like this guy, like water molecules or solvent molecules, to sort of easily sort of maybe pass through both ways. But if you try to grab something maybe a little bit bigger here, it's not going to basically fit through sort of the channel and be able to sort of get to the other side, right? Just like in our body, right? We filter out certain things, and membranes are able to kind of pass through, and some things that cannot pass through get sort of filtered out. So as we can see here, our suspensions are the red squares, our colloids are little uh, triangles, and our solutions are our circles. We can see that our solutions and colloids will go through filter paper. Again, our suspensions getting kind of caught on the filter paper. This is sort of a membrane or sort of a dialysis bag. Again, has sort of little channels that's going to allow smaller sort of particles, like solvent particles, basically, to sort of pass through. Osmosis, as we talked about a little bit earlier with calculating osmotic pressure. Again, when we talk about osmosis, there's a natural process where, again, things move from a really lower concentration to a higher concentration. So, almost like I said earlier, in an effort to sort of, kind of dilute down the more concentrated side of, say, a membrane to try to get everybody sort of in balance, if you will. Osmotic pressure, again, at some point is going to be reached where the atmospheric pressure sort of pushing back down is going to stop that natural flow of solvent molecules from one side to the next. Again, the greater the number of molecules that are dissolved, usually the higher the osmotic pressure that you have. And as I mentioned before, pure water, which has obviously nothing dissolved in it, has obviously no osmotic pressure associated with it. Here's a much better picture than what I drew earlier. Again, a brine is basically a kind of salt solution. Again, by osmosis, we would get a flow of water molecules across the membrane. As you can see, it is basically diluting it down. We could also do sort of reverse osmosis, as I was mentioning before, applying an external pressure greater than the osmotic pressure. Again, it's going to push all the water molecules back this way. Again, if you have a good amount of filters there, it's going to really filter out everything you may not want, obviously, in it. That brings us to three different ways that we can sort of describe solutions. A solution can be described as isotonic. And basically, what isotonic means is that it exerts the same osmotic pressure as body fluids. And most IV fluids are those things. So typically, when we think about what is an isotonic solution, it is sometimes referred to as being 0.9% mass to volume sodium chloride solution, sometimes referred to as a saline solution, or a 5% glucose solution. These guys are what are referred to as isotonic. And what that means is, for example, the classic example is we take like a red blood cell. And basically, if we put it in an isotonic solution, water will flow out of the cell and into the cell basically at the same rate. So you got kind of flowing in and out basically at the same rate. Everybody's happy, which is why obviously they give you those type of solutions as IV solutions, because usually if you're given an IV, you're probably not in perfect shape or something bad is sort of happening. So obviously they don't want to give you any solution that's going to kind of screw up your cells, right? And have a lot of different pressures happening and stuff like that. We can have a hypotonic solution. Hypo means less than or lower than. And in a hypotonic solution, what ends up happening is the solution on the outside is less concentrated than the, say, red blood cell, for example. So what's going to happen is osmosis is going to cause all of the water from outside of the cell basically to rush in. So if we take our same poor red blood cell here and we put it in a hypotonic solution, again, outside of the cell is less concentrated than inside. Everything from outside of the cell is pretty much going to run into the cell. It's going to cause the cell to start to swell, possibly burst, which is known as hemolysis. Probably not a good thing to happen, I imagine. We also can have a hypertonic solution. Hypertonic solution, again, means more than or greater than. And we get the opposite sort of effect that occurs. What that means is the solution on the outside is actually more concentrated than the, say, red blood cell. So sort of the opposite thing will happen in this case is if we put our red blood cell in our hypertonic solution, Outside is more concentrated. So the red blood cell, for example, is going to go, I'm going to go dilute down everything outside of the cell. And you're going to get all of the sort of water of the cell, if you will, to sort of rush out of the cell. It's going to cause the cell to start to shrink, go through crenation, also not such a good deal as well. So whether to determine, if something is going to sort of be isotonic, hypertonic, sort of swell or shrink, these are the two important numbers to remember because, again, these two numbers here are considered isotonic. So anything above those guys would be considered hypertonic. Anything below them would be considered hypotonic. Anything right on those numbers obviously would be isotonic. Question on that there. Here's some prettier pictures than my drawings there. Again, here in an isotonic solution, we got perfectly equal flow in and out of the cell, regular donut. In our hypertonic solution, we have all the water exiting the cell, donut hole. And in our hypotonic solution, we have all the water rushing into it, swelling it up like our jelly donut here, and it's going to burst in this case. So for example, if we take a red blood cell and we put it in, let's go with a 5% sodium chloride solution. Let's put it in a 3% glucose. Let's do H2O, pure water. All right, take a second and decide what will happen to each of these cells. Will they swell? Will they shrink? Will they be fine if you put it in there? All right, so let's take a look. So again, a reminder to sort of help us decide, what we're looking at here. Isotonic solutions basically consider 0.9% sodium chloride or saline. It can be potassium chloride as well. 5% glucose. So if we look at 5% sodium chloride, 5 is greater than 0.9. So that would mean this is a hypertonic solution. That means outside of the cell is greater concentration than inside the cell. So we would expect all the water from the cell basically to rush out, and we would expect it to shrink. And that is what is known as crenation. Any question on that one there? Looking at our next one, which is 3% glucose. Again, 5% is isotonic. So 3% is obviously less than that. So that would mean that this solution should be a hypotonic solution. That means that outside of our cell is less concentrated than inside our cell. We're going to get this situation right here. Everybody's going to rush into the cell. It's going to start to swell and burst, which is known as hemolysis. And lastly, we have water here. And some people go, it's water, so it should be okay. It is not okay. Water actually has no osmotic pressure, 0 osmotic pressure, which means, technically speaking, this is what we would call a hypotonic solution. And the same thing would happen is, again, outside of the cell is less concentrated than inside the cell, and it actually would start to swell and go through hemolysis. So sometimes people think, hey, water can't be bad. In this particular case, it's bad because it has, again, no osmotic pressure. So you do have basically a pressure difference. And that's really what we're talking about here. If we can kind of maintain equal pressure inside and outside of the cell, we're going to get sort of equal flow from one side to the next. So when we got that unequal pressure inside or outside of the cell, it's going to force, kind of liquid in or liquid out. Any questions on isotonic, hypotonic, or hypertonic? All right, so dialysis is a process similar to osmosis. It allows really small solute molecules, such as ions and water molecules, basically to pass through, larger particles not to. Sometimes we use dialysis bags here in laboratories, really to sort of equalize, say, your whatever you may be working on. So for example, if you wanted to do something at, say, a similar pH as in the body, and you're working with a protein, you can put it into a dialysis bag, drop it into a buffered solution at that pH, and it will sort of be in that environment, which is commonly done. In our bodies, obviously our kidneys, right, and all that stuff does some of the filtering there in dialysis, right, and kind of filters out waste products in our body. So sort of a similar type of process. And I believe that should wrap up this chapter, I think. Yep. Any questions on this chapter here? All right, so let's talk about what we got going on left here in the semester, I think, right? So Thursday is a holiday, so no class, obviously. So what we got left is December 1st, December 3rd, December 8th, and December 10th. All right, so Tuesday coming up here in a week is exam 4, or I won't say final exam, our last midterm exam, I guess they call it. It will cover chapters 9 and what we just finished, 10. So 9 is intermolecular forces, phase changes, phase diagrams. 10 is obviously everything about solutions, concentration, solubility, obviously colligative properties as well, and everything that we just talked about today. We're down to one chapter to go, which is chapter 11. So we'll do a short chapter 11 start there on Tuesday. We'll take the exam during lab like normal. We will move probably experiment 12 here, I think. And we're going to do 13 today. I'll tell you what we're going to do with that in just a second. And that leaves just one more experiment, which is experiment 14. And who knows? Maybe we'll do it. Maybe we won't do it. We'll see where we're at that point. Then we got one more. So we got a lecture here, got a lecture here, and then we got a final here, yes, which is over all of our chapters. So that is, I think, 1 through 11 in this case, happening at that point. So that is like 4 days. That ain't bad. That's a good deal. Yeah. Any questions on what's going on for the rest of the semester at this point? Yeah. Okay, so let's talk about today. So scheduled for today was experiment 12, which is magnesium and hydrochloric acid. As I mentioned, I think last time, it's not going to be a formal report. So I think we'll do it. And it's just going to be probably at that point, kind of fill in the papers that's in the manual and stuff like that and turn it in pre-lab, post-lab questions.